Okay, so this is section 15.9. This is this is the last section in chapter 15, so we're only going to have one more chapter to go. This one will probably be, well, not probably, this will definitely take 3 videos. The first video is primarily going to be developing how we get from Cartesian to spherical integrals. And I'll explain what I mean by that when we get to it. But there's going to be a conversion that we have to be able to do spherical integrals, just like when we did a conversion um, from Cartesian to cylindrical. We had a conversion factor, and we'll write that up here in a second. But that's what this one is going to be. It's going to be developing how we get to that, because I could just give you the formula and you could use it and then you'd be able to do the problems. But as you know, I like to explain where it comes from, so you actually know that this is actually legit mathematics here. So let's go ahead and talk about where this idea is going to come from. So what we have here is your basic Cartesian XYZ plane. And we've got maybe some kind of a little representative, I don't want to call it a cube, even though it looks like a cube, some kind of a representative, we'll just say rectangular prism. And if you took all those little rectangular prisms and added them all up, that would be the idea of finding the volume of that larger rectangular prism. So in Cartesian, we know this is Cartesian because it is X, Y, and Z. To find the volume of this little piece right here, well, basically it's length times width times height. Well, in this case, the length or the width, it doesn't really matter which one you call what, is delta X times delta Y times delta Z. That's going to be the volume. And then if we wanted to find the mass, we know we would take the volume and multiply it by the density. So the volume, delta X, delta Y, delta Z, multiplied by the density, which is some kind of a row function of X, Y, and Z, would equal the mass. Okay, so this is just kind of a recap of what we've done. And then if we wanted to, we could take the triple integral over E of the row function dv. Because these are x, y, and z, we could do it dv. Of course, you could do it dy, dx, dz, dx, dy, dz. There are 6 different ways that we could do that triple integral. All right, and then we learned, well, maybe there's other ways to do these things. So if we went for Cartesian to cylindrical, I'll spell it out. So basically, we would go from some dv, which we're going to call, in this case, dz, dy, dx, although it could be in any form. We know that we would get a dz, and then we would get, because of the polar aspect of it, an rd, oops, not rd, should be dr, d theta. And the important piece of information here was that r was what we called a conversion factor. Okay, it's what you needed to go from Cartesian to cylindrical. And if you think about it, and we haven't really talked about it in this way, but if you wanted to change, from one unit to another unit, like feet to meters, there's a conversion factor there. It's not 1 foot is 1 meter. They're close, but there's a conversion factor. There's some kind of a number that you multiply to get there, or Fahrenheit and Celsius. There's some kind of an equation with a conversion factor. Any kind of conversion that you do from one set of units to another set of units is usually not 1-to-1. It's usually not going to be a straight, oh, this one, then it equals this one. Is there some kind of a conversion factor? So what if instead we wanted to go from Cartesian to spherical? Well, that means we're going to take some kind of a dz, dy, dx in some one of those orders, and we are going to convert it into, well, we know that the spherical coordinates are done in rho, theta, and phi. So we're going to have some kind of a d rho, d theta, and d phi. The question is, do we have a conversion factor? What goes there? And that's what we're going to develop in this video. All right, so let's move on to second page. The nice thing about this particular drawing, and we've seen this before, is that you can get both, well, you can get all three things here. We can get Cartesian, we can get cylindrical, and we can get spherical from this particular drawing. So let's go ahead and set all these things up. So rectangular or Cartesian's easy. That's just x, y, and z. You would literally go out x over y and then up z. So that would be out x. Let's see if I can do this. Let's try and stay parallel here the best that I can. So here's x, here's y, and then of course the height here is z. There's your Cartesian. If we wanted to put this thing into cylindrical, we know that it's still going to be a height of z, but now we're going to use polar. And what we would do is we would take this distance right here as basically the radius of some circle. Some circle that could be actually formed. I'm going to erase this in a second, but it could be formed by putting a circle in the xy plane all the way around that thing. So in order to find the cylindrical coordinates, well, we know we would need r, because you need r and theta as well as z for cylindrical. You would do x squared plus y squared equals r squared, because that's going to give you your r value if you already know x and y. And then you know that because it's a right triangle, you know that x equals r cosine of theta and y equals r sine of theta. Okay, those are just standard polar. So now you have a way to find r, and you have a way to find theta. Typically, we actually use, from this one, we use that tangent of theta is going to be sine over cosine, or y over x, or however you want to put it. Y over x is usually easier if you're given x and y, and then you can find theta easily from that. So any of those formulas work. And then we can kind of use an extension of that to be able to figure out spherical. Again, this is all just review at this point. So the biggest thing is to remember that this vertical line z is going to create a perpendicular with r, which means that what's already kind of in that pink there, your rho value, is really the hypotenuse of that right triangle. So what that tells me is that rho squared is going to equal r squared plus z squared. Or if you wanted to go straight from Cartesian, since r squared is x squared plus y squared, we can replace that. And we know that rho squared is x squared plus y squared plus z squared. But we also know that spherical is rho, it's theta, it's phi. So to find theta, actually, let's go with phi, because we pretty much can figure out theta. But let's go with phi, just to give you the equations that you're really going to need here. So if we wanted to find phi, well, the angle that's phi in between the z-axis and rho, that's your angle of Bloom. But again, this is going to create the exact same angle in here, because those two things are alternate interior angles. Z or the z value on the right and the z-axis are parallel. You're cutting it by a transversal, therefore the angles that are alternate interior of those transversals in between the parallel lines are going to be the same. So that phi value is exactly the same. And within that triangle, I know that cosine of phi is going to be adjacent over hypotenuse, so that's z over rho. Then obviously you could solve that for z, so by simply multiplying both sides by rho. So you would get that z equals rho cosine of phi. Likewise, sine of phi is going to be opposite, which is r, over hypotenuse, which is rho. And if I want to solve that for r is then going to be rho sine phi. And then if we needed the x and y values, so we know that x is r cosine theta, but r here is rho sine phi. So x is r cosine theta, r is rho sine phi cosine theta. And y is r sine theta, so that's going to be r, which is rho sine phi sine theta. All right, all of that is pretty much what we've already done. Now, we do have another idea that you probably have not seen for quite some time. So we'll call this the other idea. This is going to take us all the way back to probably geometry, maybe a little bit in pre-calc. It says, if I were to have a radius and another radius coming out from the center of the circle, so these are the same value, then this piece in between on the outside of the circle is the arc of that radius. There is an angle in between, and we typically call this arc S. And if you happen to remember the formula, great job. If not, the length of that arc is simply r theta. It is the length of the radius times the angle in between the two. And I guess probably the easiest way to, it's not really a verification, but to think about it is, one of the most common ones that we know is that if we talk about what if the arc represented the entire circle? Well, then theta itself is 2 pi. So the arc is r times 2 pi, or more commonly seen as 2 pi r. That's the circumference of a circle. So any portion of the circle, as long as you know the angle in between the two radii, in radians, it must be in radians, then it's the arc length, or the length of the arc on the outside, is the radius times the angle in between. All right, we are going to use that in developing our conversion factor. So stick with me, we're getting there. All right. There was no way I was trying to draw this one by hand, which is why I pulled it straight out of a book. The idea is, if we're going to use spherical coordinates to be able to do these integrations, so we're going to have to convert things into spherical integrals. What we have here is basically a spherical wedge. And that's what we're going to call this thing. This is a spherical wedge. And what you should notice is this is not exactly a box. It's close, but it's obviously got curves on it. It's not exactly straight edges. But what you really want to think to yourself is, if you make these so incredibly small, because obviously what we're going to try and do is add up all these spherical wedges as part of our triple integral. If you make these so incredibly small, it's basically the volume of a box. So we're going to say it's not going to be the volume of a box, but it's going to be approximately length times width times height. And again, the smaller you make them, the better. Okay, so here's what we have to do. We have to break this into its three pieces, because we know we've got a rho, we know we've got a theta, we know we've got a phi. That's all a part of how this thing is going to work. And another thing is, again, what you want to do is you want to make these things extremely small. So as you can see, there is definitely a thickness to this spherical wedge. As you make it really small, the thickness basically approaches zero. It won't have a zero thickness because if you think about it, you're taking you know, the outside of a sphere. It's going to have a thickness. We just want to make it extremely thin. So let's kind of develop this. If we were to look at the rho part, try and do this in different colors here so we can see this. So if we're to look at the rho part, rho is the length from the origin. Whoops, I did not mean to do purple, or at least not that kind. Rho is from the origin out to the edge of the box. But there's technically two edges of this box. So it's not only going to go out to that part, it's also going to go out to the top. So what you're going to have is with these particular pieces right here, these pieces right here are going to represent your rho angles. I'm sorry, your rho lengths. And what you've got in between those is going to be some kind of a delta rho. You've got a change in your rho values right there. All right, so I'm actually going to erase kind of the marks that I made there in green because that's actually going to represent something else. But I just wanted you to make you see that it's from the green one to the green one. So really the distances are here. Let's put this in red now because I want it to be in red. So that distance right there is your change in rho. So we're going to say that the red distance here is the change of rho. Let's erase that one too. It's supposed to go all the way out to the edge. There we go. So that's the change in rho. So we're going to have a delta rho. And those are not bad because they're linear. Okay, so they are straight lines. They're not curved. It makes it pretty easy. That's pretty straightforward. But then we also have, let's do this in blue. We also have a change of theta. Well, theta is the angle which is made in this direction. And it's these curved pieces right here. And if you project it down, which is what they did here, they projected this thing down into the XY plane so that we could kind of see what the change of rho is. Well, look at this. These distances here are R. This piece right here is the arc. So you've got two radii and an arc. So this piece is basically S. Okay, so let's just kind of take that and we're going to blow that up over here. So we had our R. We've got some kind of a change of theta in here, and that's because if you think about it this way, if your first angle was 0 and your second angle was whatever it is, we're going to call it theta, then the change of the angle is literally theta. But if the first angle is not 0, so if it's two separate angles, then what you technically have is you have an angle which goes to here, another angle which goes to here. So the angle that's created in between them is really the change of theta. So that's what we're going to have here. And according to this arc, that piece right there, which is kind of like our width of the box, I guess if you want to say, or the width of the spherical wedge, since we've already got the height, this is S equals R theta. So the blue one, whoops, come on, there we go. The blue one is going to be some kind of R times the change of theta. So it's R delta theta. But remember, we're doing this in spherical coordinates, so we don't have r's in spherical coordinates. So we need to change r into a spherical coordinate. Well, fortunately, from our previous page, we have that, because r is defined as rho sine phi. That's in rho, phi, and theta. So we're going to replace r with rho sine phi. So that means that we're going to have rho sine phi delta theta. Okay, so that's going to represent basically what, again, would be kind of the width. And then we have to deal with the length. Technically, we could have called these things anything, but the length is going to be the change here. You're going to have changes in this direction. And your change is going to be a change in your phi values, because you're going to have one angle that comes out to this side, and then you're going to have another angle that comes out to that side. So you're going to have a change in your phi values. I'm going to erase those because it's getting too sloppy. It's the same general idea, though. So here, what we're talking about is really the difference between this piece and this piece right here. So this right here, I'm just going to use this one in particular because you've got one at different places, is also it's also a sector of a circle, where this value is a rho, this value is a rho, and then so the end of that is going to be an S. So I'll put that over here in orange. It's exactly the same idea. This was rho, and this over here was S. But again, the arc is going to be the length of the, in this case, the radius is rho, there we go, times the change of the angle. And this angle in here was a phi, so that's a delta phi in there, so delta phi. So the orange part is going to be rho delta phi, and those are perfectly fine to leave because those are already in terms of spherical. So length times width times height. Length times width times height. So when I go to do our conversion, our change in our volume is going to be, let's see, what do we got? We've got delta rho sine phi delta theta times rho delta phi. So typically we're going to put all those changes on the end. So we're going to have, let's see, I've got a rho and another rho. I've got a rho squared. I've got a sine phi. And then I've got delta rho, delta theta, delta phi. So there is your conversion factor right there. So could I have just given that to you and let you use it? Absolutely. But I figured I needed to spend 25 minutes or so doing this just to let you know how it all works. Just kidding. So here is our ultimate conversion in the end. So if we take a triple integral over E of some kind of a function, dz, dy, dx, we'll just put 1 in here for now so that we're just going to say volume. That is the same in spherical as the triple integral over E of rho squared sine phi d rho d theta d phi. And there we have it. Okay, so on our second video, we'll come back and do a few examples, and then the third video, we will finish this up.